Welcome everyone for the tACS challenge committee. This will be there will be a series of presentations on this in this meeting, and I would just like to kick us off. So I'm going to share my screen, but I'm not able to share my screen because the host disabled that. So can you share your screen, Till Ola? Now I can share my screen. Okay, fantastic.
Hi everyone.
Hey, Neil.
Okay.
How are you all doing?
Here we are.
Doing good.
Hi.
All right. Very good. So, yeah, welcome everyone to the tACS Challenge Committee. This is sort of a business meeting where we just try to update ourselves and everyone interested in this initiative to the current state where we are. Obviously, progress has been a little bit hampered by the pandemic, but we did actually make some progress. We did do something, as you will see. So that's the roadmap. So I will give a brief introduction, and then we will hear about montages from Axel. We will hear about the Arduino box by Neil Grossman, Eddie Rhodes, and then Till Ole's lab and Christoph Hermann's lab will talk about piloting. We will also briefly talk about our piloting experiments, as will, I think, Carlo might also want to say something about their pilotings. Yeah, and then we will have a general discussion, and in order to allow enough time for that to happen, I just quickly move on. So just to briefly recap the tACS challenge, it's a international multi-center initiative to test for online tACS of tACS, online effects of tACS on behavior. And these effects should result from phasic current modulation in the brain as opposed to sensory confounds, which we heard already a lot about in this afternoon session. This is very much a grassroots movement. So it started at the meeting that happened in Cambridge, I think 2 years ago, or was it 3 years ago? I don't know. I think it was 2 years ago, the paper meeting in Cambridge. These were the initiators in alphabetical order, but just to highlight, if you want to get involved, then you can absolutely get involved more if you want, more than just data collection. Just let us know. So this is open to anyone with an interest in this. We have a Twitter account. Follow us to stay updated. We also have the current protocol and other documents on open science framework. So this is also very much an open science initiative that tries to adhere to all the transparency principles. And if you email, and there is also an email address where you can email us. Okay. So we already have actually more than 30 labs signing up, distributed in the Western and Eastern hemispheres and the Northern and Southern hemispheres. So it is fair to say that this is probably the biggest worldwide brain stimulation experiment that at least I know of. And again, if you want to join in, if you think you would also like to collect some data and join this initiative, then by all means do get in touch and email us. And obviously a big thank you to everyone who has signed up so far. So without the participating labs, this initiative wouldn't be where it is, and it wouldn't be happening. So that's very cool. Okay, so what is the idea? So the basic idea that we want to test in this experiment is that tACS modulates cortical excitability and perception. The basic concepts we already heard, and they were very nicely illustrated in the previous talk, but just to briefly recap on a very, very simple basis, the idea is if you have a neuron and its resting membrane potential would be somewhere there, and say this is the spiking threshold of this neuron, then we would induce a current with tACS, thereby bringing the neuron closer to its firing threshold or pulling it a little bit away from its firing threshold. And the idea is that if you have a synaptic input that arrives at a particular phase, then if that is closer to the firing threshold, it might actually bring the neuron to fire. So the neuron would be more likely to fire when a synaptic input arrives in this phase. And if it arrives at that phase, it would elicit activity that's below the threshold, so the neuron would not fire. That's the very simple idea that we would like to test. In humans, of course, we don't measure neurons in this non-invasive experiment, but we can measure the behavior. And from that simple hypothesis, it follows that if you present a visual stimulus at different phase angle, you should see a modulation of the ability to detect that visual stimulus, such that when you present it more closer to the firing threshold, it should have a higher likelihood in being detected as opposed to when it's more pulled away from the firing threshold. Therefore, the hypothesis is that perception performance varies as a function of tACS phase. So that is the idea of this experiment. And yeah, there will we had lots of discussions on what is the best way to place these electrodes, and we had fantastic input from Axel Thielsche, and he will talk about these montages briefly in a minute. So I just quickly go over there. In essence, we have an occipital montage where we target the occipital cortex. That's of course the montage of interest. We have a retinal control stimulation where we mainly target the eyeballs. So that is one of the important controls to control for influence of phosphenes. And we have a cutaneous control stimulation where we mainly stimulate the skin under the electrodes, but less so the brain. So this is to control for the transcutaneous effects that Miles and Chris talked about. So these are the three conditions, and yeah, it is important to control for these obvious side effects. So we have the phosphene control and the cutaneous control. With the occipital montage, we aim to stimulate with 2 milliamps peak-to-peak amplitude, or at 90% of the individual maximum intensity without phosphenes and without rhythmic cutaneous sensations. So subjects will fill out the questionnaire that allows us to stay below any of these sensations, essentially. Yes, so some labs will be able to use topical anesthesia. So for instance, we have used Emla cream, and I think Till Ole's lab has also used Emla cream. And they can use this cream to allow for higher stimulation intensities, hopefully inducing stronger effects. But we obviously acknowledge that some labs might not be able to use the cream because of local ethical restrictions, or because it's very complicated to get ethical approval for that. And these labs should still participate, of course, in the initiative, but they then will just use slightly lower stimulation intensities. We have questionnaires that will be filled after each block with respect to the phosphines and the cutaneous sensations, so that we can track these effects. The behavioral paradigm that we came up with, I call it sort of half smiley face paradigm. So you have a fixation dot in the middle, and that is actually an LED. So what you see here, the white dots are LEDs mounted on a cardboard. So you have a fixation LED in the middle, and then you have 5 LEDs in this half moon shaped around the fixation. The participant should fixate here in the middle. And then one of these LEDs, and the participant doesn't know which one, will change its luminance for a brief period, 10 milliseconds, we suggested. And the participant's task is to detect the change in luminance and make a button press. And yeah, the intervals between these luminance changes will be between 1.5 seconds, 7 seconds, although we have a log linear distribution, so the mean is around 2.8 seconds of inter-trial interval. And that's the task, so it's a very simple visual detection task. We stimulate with our conditions, A, B, C, in a Latin square kind of fashion, where we counterbalance the position of conditions with respect to when they occurred across participants. So we have 9 blocks, essentially, each block lasting 7 minutes. And we stimulate throughout, although it should be pointed out that the actual that only one of the 3 stimulations actually stimulates the brain, because the phosphene control will mostly stimulate the eyeball and the currents will be minimal. Almost no currents will go into the brain, and the sensory stimulation, where we just pass currents between the skin, will also have a very minimal stimulation intensities in the brain. So effectively, we only stimulate the brain with one of these conditions. That's important to know. And altogether, we estimated here the time being 80 minutes, although what we do not mention here is that there is a questionnaire in between here. I did fill out the questionnaire. It took me about 2 minutes, so I think we can add a further 10 to maybe 10, 12 minutes on top of these. So it will take us more closer to 90 minutes, a little bit over, I think. The idea is that we backsort the stimulation, the onset of the luminance change to the phase of tACS where it occurred, and then relate this to the behavior, so to the ability to detect the change. We, of course, with any such paradigm, you're naturally worried about timing. In order to get around this issue, we use one box to control it all, to use a Lord of the Ring metaphor here. So we have the Arduino box, which essentially records the tACS artifact. So the tACS will be applied by whichever tACS machine is used in the lab. And the Arduino box records the tACS signal, it records the button presses, and it also controls the stimulation. So that should ensure a near perfect timing. And we will hear more about the box from Neil Grossman's lab, who built the box. So where are we in this big adventure? So the first step would be to build the control devices and program the task. The next step then to get this off the ground is conduct technical feasibility pilots. Of course, that's been hampered by COVID, but we did make some progress, as you will see. Then we finalize the experimental protocol, and then we can draft the registered report. So far, the plan is to submit the registered report to Nature Human Behavior, which did show some interest. Then we submit the ethics proposal. So each center submits their own ethics. That would be the idea. And then we would submit the registered report, stage 1, to whichever journal accepts the registered report. And then we conduct experiments. So then we can actually start collecting the data. The data will be combined in a way that respects data protection laws. So it will be in a pseudo-anonymized form, where we only share essential data, individualized or demographic data will not be shared on an individual basis, and we don't need to, so we don't have to then do that. Then the data will be analyzed by using an algorithm that Benedikt Zöfel has shown in a paper to be good. So we just trust Benedikt and use his algorithm. We all send him his data and he will analyze it for us. And then we run the statistics per lab and we pool it. And we will use frequentist approaches as well as Bayesian approaches, which we can do with because we hopefully will have a very large statistical power. So we can actually get a true estimate of effect size. And yeah, then the results will be discussed and we're going to write it all up and publish it, hopefully. So where are we in this? Well, the box has been built. It has been shipped to 4 labs so far, as far as I know. So Till Ohler's lab has one, Christoph Hermann's lab has one, Carlo Minussi's lab has one, and we have one as well. And so we can do technical pilots with these, and that is currently happening. Yeah, all the other steps we haven't started on them yet. So at the moment, we're still at the very beginning. And we will hear more about what has happened in the technical pilots later. Okay, that's already it. So that was the update and the brief overview. And we next will hear from Axel Thielscher on the update on the tACS montages and stimulation. So Axel, please unmute yourself and get started.
So, hi.
Hello.
Hey there.
Hello. Just a second, please. So let me share my screen. I want to give a short introduction on the montage of the tACS, and basically discuss a little bit the thoughts which we had when we actually designed this. So for that, I'd like to share my screen. Just a second, please. Let me share my screen. Good.
Great.
Yes, perfect. So let's minimize this here. Good. So basically, what we aimed at here is a montage which is very specific on stimulating early visual areas, as shown here. This is just from one review paper, but this is really textbook knowledge. And as you have seen how the visual presentation looks like, and this is also was designed like that on purpose, because when you arrange like a fixation cross here and then have the LEDs arranged like that, what you will do, you will then have the activate the early visual areas here in this region. So basically, when you have the lower visual field, and you activate the dorsal early visual areas, the dorsal parts of the early visual areas. But that we have a very good control of basically where we would like to then change neural activity via tACS. So our goal was now that we achieve a very homogeneous field here and strong field in this region, and which is in phase also, so not like phase flips in this region, and that we achieve this by having a standard two-channel stimulator. The goal there was really that everybody who would like to join with standard equipment can then also join this challenge. At the same time, we wanted to also minimize the co-stimulation of the eyes. This was a further requirement, and the montage should have been designed in such a way that we can control properly for continuous effects. So then let me show what I came up with, or what we came up with here. So this is now how the montage looks like. As you have already seen, there are also two electrodes in the front. Here we have these three electrodes, which are then basically covering the area, the skin area above the area which you want to target. And we have three return electrodes. And by that, we already, as you have already shortly seen, we have a nice focus here of the fields. They're relatively strong here. And as you also see here, so blue and red depict opposite phases here of the current flowing either in or out of the cortex. And we have a nice homogeneous red here, meaning that at least in these regions here, we will have all the effects will be all in phase. Obviously, this is not perfect. When you rotate a little bit, then you see that there's more blue, also a little bit of blue also here. But overall, we achieve a relatively homogeneous stimulation of this area which you want to have. And also in the frontal areas, actually, it's relatively weak. As a comparison, I have here simulated a montage which has only one electrode, one return electrode here. And what you see here is that for when you have only one return electrode, the fields gets much more broader, which you have here in the front, and also the eyes get a stronger co-stimulation than here. The co-stimulation here is not very strong, but as it is known that it's actually sufficient to often induce really phosphenes by stimulation of the retina, and this is much better than here, basically. In practice, what can be done here is that we just really connect the three electrodes here to one channel and those three to the other channel. So it's very simple, and this can be done basically via a normal two-channel stimulation. We also have then two more electrodes here on the cheeks, and which allows us to do a very efficient retinal control stimulation by then stimulating with the return electrodes here. And those, again, these two would be linked to one channel, and these three to another channel. As you see, the eyes are really red here, which means that in order to get phosphenes which are on the same level as you get with the original montage, you will be able to use very low current strengths, meaning that also the co-stimulation of the brain will be minimized. It will be a relatively clean control for retinal effects. The last thing is that we wanted to have a control also of the cutaneous stimulation effects, and for that, that's actually one of the reasons why we have three electrodes here in the back. One reason is that we make the distribution of the field a little bit broader to cover these areas homogeneously. But it also allows us actually to then link two of these electrodes to one channel and the other one here to the second channel. When we do that, we really have most of the current flowing through the skin, as I'll show in a second. And only a little bit of the current is then really entering the brain. And that's something you see here when you compare, again, the Vero montage with this control, and you see that there's, for the same current strength induced in the electrodes, there's really a massive reduction of the currents in the brain. So that's good. For the skin, it's the opposite. So here we see that because there's a lot of shunting here in this region, the amount of continuous stimulation in the region of the main electrodes here should be very strong, so that we can hopefully easily match the level of cutaneous effects which we see for the main montage. And the hope is really that this can be done at current levels which are at least not higher than what we need for the real stimulation approach. Preferably, it would be lower, because in that case, we would then even lower the amount of co-stimulation which we have in the brain. So from a simulation or from a simulation point of view, it would be really interesting to get now a little bit of data from the pilots on how strong this control montage has to be done in terms of the current strength, so that we can adjust a little bit the simulations and see whether we can really avoid cortical stimulation with this montage. So this is a little bit the thoughts about, behind the Montage, which we use. So that's why it's a little bit more complex than it's often used in other tACS or tACS experiments. The goal was really that we try to be as clean as possible with our control conditions and avoid side effects as good as possible. Yeah, and thanks. That's basically what I just wanted to say about the Montage.
All right, thanks, Axel. Fantastic. I think Nia and Eddie are next to talk about the Arduino box. So Axel, if you could stop sharing your screen, then I suppose Nia should be able to share his screen, or Eddie, I don't know which one will be talking. So please unmute yourself and...
Yeah, I will do that. Let me share my screen. Can you see my screen?
Yes.
Excellent. Good afternoon, everyone. We put some presentation of the hardware we developed for the tACS challenge, and it's a big introduction. Here and I have.
You just got muted. Can you unmute yourself?
Yeah, I did. Can you hear me now? Excellent.
Yes.
So the requirements that we had was to develop the hardware that allows us to conduct the LED visual threshold experiment with this particular requirement in a very high resolution. Since we are measuring response time, so temporal resolution was important for us to do it in a way that it could be robustly deployed across labs and in a way that is easy to use. So I will take you through quickly the hardware implementation. So the hardware has, as I showed before, has a control box and the LED display. So in the control box, we have essentially two buttons that are at the moment treated equally. We just thought to enable this extra feature so the subject can, or the participant can press each one of them. This is how we capture the response of the subject, of the participants here. We have means to record the voltage waveform from the tACS or the electrical stimulation on the head. So that the idea is we'll have two kind of an EEG surface electrodes on the head to pick up essentially the artifacts from the stimulators, and this is and we will record it via this port. So this is normal, taking normal EEG recording electrodes, and what the motivation behind us is to allow us to do later on kind of more basic computation when we have the actual waveforms of the stimulation. So this is the other side of the back side, essentially, of the control. This is just a place to get the external battery for the LED and the control. So we don't sync too much from the computer or laptop. This is a trigger in and out. So the BNC-based trigger to allow to synchronization with the stimulation hardware as well as EEG hardware if people doing EEG simultaneously. And this is the interface to the LED array. And this is the interface with the computer. This is the implementation of the LED array. It's basically designed to cover about 0.7 degree of the field of view at a 1 meter distance. This is how we design it. I mean, this is a specification for its previous studies. It has essentially, we end up in having this kind of a mounting configuration that essentially allows to put the LED on any of these monitors. Here's an example where we're mounting it on a simple on a laptop. the configuration of the LED is precisely made to have the right. So each LED is about 3 millimeters, has a thick distance, as I said, and kind of this a half circle to cover the 0.7 degree. We have in the middle a fixation LED. In this control script, we labeled it LED number 0, and then we have 5 basically test LEDs. So during the experiments, as Simon was saying, all of them will be on, and then we change the intensity of one of them in a random intervals and a fixed rate that we determine in kind of calibration, threshold calibration procedure. I will talk in a second. This is the graphic user interface. It's a Java base. On the control box, there's essentially tNC Arduino microcontroller that essentially interface with this Java software or GUI. And so quickly, what we have here is this is the ability. This is where we set up the communication with the control box. This is here we define in 3 and 4. We define the path to the folder where we want to save the data that we log. The 5 will be, this is where we essentially can visualize the voltage that recorded on the head from the tACS stimulation. And this is the display of the LEDs, so the voltage. So we have the 0 and then another 5 test LEDs. This is a display in real-time display of the button press of the participants, and this is a visualization of the PNC of the trigger going out. All of that is controlled through a script. And the aim here was to give us a maximum flexibility. So let's say in the future, we come up with another paradigm, potentially we can deploy it in, or need to make changes. We can do that very quickly here. And so the control is done via script. We can write the commands here and send them, or we can load a command file, which is essentially a text file, here and run it. And I'll show you an example. And here, this is just a display that allows to see what are the commands that have been sent to the control box. So here's an example of a script, and I won't go through all the commands, but in principle, what you can see here, we start logging a file, or we open a file that we want to log. We call it block. It's just the name of the file. And then we declare, in this case, we declare parameters. And we say basically parameter baseline is 0.1 and increase is 0.2. We can define up to 20 basically variables in the device. That means that we can refer to them rather than setting up actual values of the LED's intensities. In this line, what we are seeing here, we are sending essentially a trigger out of about 3.3 volts for 100 milliseconds. And then this line of code essentially setting up orders of LEDs intensities and displays. So for example, so this will be, this is the command called the LEDs, and then this corresponds to the value of LED 0, LED 1, LED 2, and so on. And that will be how long this basically will be maintained. So in our case, baseline represents 0.1. So the intensities of the LEDs are all normalized between 0 and 1. So here they're setting to 0.1. And then after 2 seconds and a half approximately, it will change that. So the LED number 2, so this is 0, 1, and 2, we now change into intensity for about 10 milliseconds, as you can see here, for the value of 0.2, and so on and so on. So that's why we set it up. Here we actually execute it. So here we execute essentially this command, and then we go seriously across them, and then when it's finished, we basically have to close the file. Okay. Here's an example how it looks like. We loaded these commands. We can see them here. We execute them. So this is just a noise, of course, but here we will see the tACS waveform. You will see here, for example, we see LED 0 is on, and then immediately after LED 2, this is LED 2 coming after in the shorter, smaller intensity. These are the buttons. So the subject press a button here, corresponding potentially to LEDs, one of the LEDs. And this is the trigger out going on and so on. As I mentioned, there is a routine here in which we identify the threshold, because we are basically having a baseline intensity, and then for 10 milliseconds or short period, we change intensity of one of these LEDs. So to identify the subject specific, basically, intensity or target intensity change, we implemented the adaptive staircase, basically algorithm. There's a user interface for that, but can be controlled essentially via script. And I won't go into details. There may be other people after me that can describe it. But fundamentally, the output of that will be these two intensities. A variable contain the original, the starting baseline, and intensity of the LEDs, and B is essentially that plus an adaptive target brightness that was found during this this routine. And then the control works maintain these values. So when we run the script, we can refer to them. That's all. Just to acknowledge the people that actually did the work. John, who I think is with us here, developed the hardware, and David, my colleague, is developed the experiment software, and Eddie contributed a lot in testing and guiding this work. So thank you.
Thanks, Nia. Excellent. So it's, this is really super important that you produced this device and shipped it around, and it's going to be the core element, basically, which also ensures quite some standardization across labs. It will really make things easier. And I think it's my turn next. So I'm going to present our piloting work using this device, actually. So let me share my screen. So does it work? Can you see my screen? Excellent. So also, first of all, thanks to the tACS Challenge piloting team in Mainz, and most of all, Umer Hassan, maybe you want to unmute yourself, or actually at least show you on camera. So he did all the work, was really instrumental to the entire piloting experience we had here so far. So I'm going to show some piloting results on the perceptual threshold determination, the phosphene and cutaneous threshold determination, which we tried, the tACS signal recording from the scalp, tACS electrode montages, and possible problems we might encounter there. Then the montage switching procedure, where we propose a solution, and some further observations along the piloting. So here's a setup, exactly as Nia envisioned it. It's mounted on a monitor, and the participant is sitting, well, I think it's not in meter distance here, but in principle, sitting in front of it and is able to press a button with the right hand. I think we have to decide whether it should be the dominant one or with the right or so. So that all works fine. As we need to discuss, maybe the LEDs are pretty bright, and some subjects had difficulties with the brightness level, especially when the room lights were actually dimmed, but I'm coming back to that. Tried a few titrations in a number of subjects here. There's one subject where the baseline LED intensity ranging between 0 and 1 was set to 0.1, because otherwise it was experienced uncomfortable. But I think we also had the room lighting too dark until now, and we should make it actually more bright, so that the difference to the LED brightness is not so strong. And then the difference was titrated that was needed as a change from this 0.1 baseline intensity. And since Omar thought maybe it might actually make a difference whether tACS is applied at the same time or not, because the the sensations you might have might distract you, for example, or might actually facilitate any kind of perception. We also did it with and without tACS applied at the same time for the 3 different montages, montage A, the occipital montage. We got the difference, so just noticeable differences of 0.1, 0.08, retinal montage 0.2, 0.1, for the cutaneous control montage 0.19, 0.07. So at least in this subject, it seems like the thresholds, or actually the just noticeable difference, was always a bit smaller when tACS was applied at the same time. But I wouldn't draw too many conclusions from that already. So we need to do a few more pilots, more subjects, to see whether there's a systematic effect that we need to take into account. And of course, I think that we also should maybe start the titration at a level that is close to the baseline level, so that we do not waste too many trials by just getting down to that level, right? But these were just the first attempts. In principle, it's working. It's important. Then we tested in 2 subjects the phosphene and cutaneous sensation thresholds. Cutaneous sensation here refers to the intensity where you start feeling rhythmic sensations, because we thought, okay, if you feel some continuous sensation, that is fine, that's not going to entrain, but it shouldn't be rhythmic. And again, the question was, okay, is maybe the threshold also depend on whether you do the task or not, because it might make a difference whether you you look at bright LEDs or are attentionally focused on a task or not. Luckily, so in the 2 subjects, it doesn't seem to be the case, which would be good news, because otherwise it would complicate maybe the titration procedure for the phosphene thresholds and cutaneous sensation thresholds. And what we see here is actually exactly how it was predicted and wished for by Axel. So in the occipital montage, we get, basically it was just increasing in intensity in small steps, like 15 then 25 microampere, until these sensations were reported, and then checking before and back. And so in the occipital montage, at some point, the subject reported rhythmic cutaneous sensations. In this case, at 1.7 milliampere, or here 2.1 milliampere, while no phosphenes could be elicited at reasonable intensities. That's actually good news. The retinal montage is, as expected, at much lower intensities, able to produce phosphenes. So at 250 or 150 microampere already, but it's not producing any cutaneous sensations, which was also not clear, because the skin is pretty sensitive here around the eyes. So that worked fine. And then the cutaneous montage, actually, as predicted, higher intensities, but still lower than for the occipital montage, and was not possible to produce phosphenes, only cutaneous sensations. So that is well in line with the planned way of setting the intensities, namely finding the intensity for the occipital montage that gives us like 90% of the, in this case, rather cutaneous threshold, and just retinal and cutaneous control montages accordingly, so that it would stay at 90% of the phosphene threshold or 90% of the cutaneous threshold.
Till is this peak to peak?
I'm pretty sure, I think. Umer, maybe you can comment on that. Is that peak to peak intensity? Or
Yes.
No, it's base to
peak.
Yeah.
Oh, really?
No, this intensity is peak to peak. This intensity is peak to peak.
It's peak to peak.
Yeah.
Okay. Yeah. Good. Thanks. So then I tried to record the signal from the scalp, and we tried just 2 different bipolar montages to see whether one of them maybe works better and has better signal to noise ratio. The red channels here are the EEG or just scalp artifact electrodes, and we just use standard EEG electrodes, multi-electrodes from EasyCap. just simply using the same gel, the 1020 gel, and attach them to the respective sites. That's how it could look like. It doesn't need to be too precise, or it's not about EEG. And here you see the recordings of two different montages, POZ versus CZ or POZ versus FZ for montage A, B, and C, so the three tACS montages. And because they have different current intensities, montage, and the physical distance of the recording electrodes to the stimulation electrodes differs per montage, obviously, we get very different signal to noise ratios. So it's always here min-max scaled, and it's more about the noisiness than about the absolute amplitude, because that's irrelevant. So POZ ZZ seems to work pretty well. And the good thing is we can use the strongest bandpass filters as long as we do not produce phase shifts later on, right? We can even fit a sine wave. So it doesn't matter whether it's a bit noisy. We don't care, right? We know it is a 10 Hertz sine wave, so we can definitely easily get a nice phase from the signal. And that's what we wanted to test, whether this scalp signal can be used to determine the phase. Importantly, the device needs to be positioned in a way that the hand and any movement of the subject is not interfering with these EEG electrodes that are inserted here. So maybe for a left-handed participant, you want to turn it around, use the other button, make sure it's not moving around, because that will disturb the signal. So tACS electrode preparations, we use the 4.5 centimeter round electrodes and the 2.5 centimeter round electrodes from Neurocare, and 1020 gel, which the 1020 gel was applied on the scalp and on the electrode, and then it was like a sandwich connected to make sure that there's good connection everywhere, despite the presence of hair, which is always an issue. We can just use an EEG cap to find the positions, make a dot, make a circle around it maybe, and then you know which area to prepare. You can already see a possible issue here in these two participants, two smaller female heads, like 56 EEG cap size, I assume. And the distance, the physical distance between those electrodes might be too small. I think this issue has been raised earlier also by Carlo already, and it might actually be a problem. So we might need to consider either small electrodes or just move the outer electrodes slightly away from O1, O2, a bit more lateral. So I think we should discuss this, Axel, and maybe do another simulation to see whether that would be okay, because we need to prevent any kind of short circuiting due to too much gel or then sweating or whatever. I mean, for the occipital montage, that would be fine, even, but for the cutaneous control shunting montage, this is crucial that it works. Okay, so to keep everything in check, we applied those net bandages. Here you can also see the position of the two smaller electrodes below the eyeballs or on the cheek. And I think it looks pretty tidy once you have the net bandage on it. And the 1020 gel is very sticky, and this bandage will also help that nothing is going to fall off. Now, switching the montages, right? I mean, we always need to have 2 or 3 montages in one channel, 2 or 3 electrodes into one channel, and this has to change after each block. So either we use like tons of those connectors, and it gets very messy, and human error is going to happen, or they will just fall off. Or actually, we'll use what Umer designed and built, which is a montage switch. That would be possible in 2 different ways. One is a passive switch, which means there's like has these 4 sides. On one side, the input from the tACS device is connected, and then you can connect the cables for the occipital, central parietal, and eye electrodes, and you have to switch it around in that box. Still better than a lot of small links that can fall off, but it still means manual work. but it's the same as just using those Y connectors or so in terms of not a big change to the circuitry. Or, which I would actually strongly prefer and which we're going to implement, is an active switch. So here, the current is actually actively routed to the respective montages by setting the resistance of individual routes to an infinite level and basically blocking the current from going in one direction. So it's not really interacting with the currents, but just routing the current flow. And it can be triggered, some montage switches can be triggered by TTL pulses, like 1, 2, or 3 pulses could decide about the montage. And the Arduino device has such an output, so one could easily just fully automate it and completely remove human error. The good thing is the passive and active boxes would cost like 15 or 20 euro to produce, and as long as it is a limited number, we would be happy to take care of that and ship it around. Oops, okay. So final observations. I was already mentioning the discomfort when there's too dark background illumination, and so the subject even reported beside discomfort in their eyes and like a negative impact on the mood and motivation to continue. So we might need to find a good level of lighting. Maybe even individualize. We need to discuss whether that will cause problems and additional variants. The questionnaire at the moment, like it's a 2-page questionnaire and it takes time to fill in, and especially after looking at for several minutes at these LEDs, the participants even had trouble focusing on the questionnaires, and it had to be read to them by the experimenter, and they just mentioned what they want to fill in, and actually they would have preferred to just mention then after this second or third block just the changes and not fill it in every time. So we might need to make this a bit more feasible. So it's possible that the visual perception threshold changes during the task, and I think we also decided that we need to retitrate. That's something we need to look into. Questions whether we want to give any feedback on task performance, because otherwise you're just doing your thing and you don't know whether it's correct or not, and this is also have a negative impact on the motivation. And we need to discuss like how do we want to measure actually the impedance, because measuring pairwise impedance after the preparation for all the electrodes would take a long time, and if you want to monitor that over time, that will take too long. This would be the questionnaires at the moment, and maybe we find an easier way to fill them in or have them provided digitally, or I don't know. We need to discuss that. Okay, yeah. So thanks again to my lab for doing this work, and that was my part. Maybe I should we wait with the questions until the very end to just make sure that we get all the presentations done?
I think that's a good idea.
Yeah.
Yeah.
Okay, then I stop sharing now.
That's what we have the discussion for, but
yeah.
We should carry on. We're already a bit behind time.
Yeah, that's right. We can still use the break.
Yeah. So Christoph, Florian, please unmute yourself and take it away.
Florian is going to present.
Yeah, and hopefully you can see my slides and myself and you can hear me. Yeah, okay, great. Yeah, so I will show you the Oldenburg experience that we had with the Arduino device. We did not as thorough piloting as Till Ole did in his lab, but we did some technical testing, and we did 2 or 3 quasi-realistic recordings. So we asked someone to do the task, used the device obviously, and we applied tACS, but not with the dedicated montages that Axel provided us with, but with a simpler CZ/OZ montage, so we can see how the EEG electrode, these quasi-EEG electrodes would pick up the currents. And some general impressions that I would like to share. Due to the Corona situation, I had to switch back and forth a bit between my personal computer and lab computers. So I was actually able to test the device on different operating systems, and it worked quite well on Windows 7, Windows 10, and on Mac, which might be of relevance if we want to do it multi-center. What I don't know yet is how well it works with Linux. Maybe if any of you tested it, feel free to share your experiences. Yeah, and the GUI and the Arduino worked very well. We encountered some problems with the MATLAB scripts because they had some operating system dependent or some used some system commands with which caused some issues, and I heard there were also issues with some MATLAB versions.
Florian, are you actually showing slides at the moment? I only see our main building, but no slides.
You don't see this?
I see the main building of our campus and only a bit of it.
Okay.
Yeah, that's better.
That's better. Okay. Yeah, there were some problems with some of the MATLAB scripts that came with the device. But as Nir pointed out, the actual syntax of the GUI is quite easy, and it's very easy to actually write your own scripts to control experiments. And actually, there is now a new script available that I created in response to this, which you can now download in the Dropbox folder that Eddie created. So if you have use for that, feel free to use it, and also feel free to come back if there's any room for improvements. Generally, it was very easy to set the device up. Things are easy to handle. For installation, it may make sense to have the documentation available. And it's definitely a great device, and I also see some future applications for other experiments. What came to my mind while testing was whether if we want to do this in a multi-center approach with 30, 40 labs, if the flexibility that the device currently offers is actually desirable, or if it might make sense to log parameter or hard code some of the parameters to avoid or reduce the risk of human errors. You may disagree on that with me, but I just wanted to offer this as a discussion point. Another thing that we've already seen in Ole's talk is we also experienced or had some concerns with the recording electrodes. Their range is relatively limited. And so depending on how you place the electrodes relative to each other and relative to the stimulation electrodes, they may not pick up the signal or run into saturation, which then would obviously cause problems for us for the analysis. But what Ole just showed in his more sophisticated analysis looked quite promising. Another thing that happened in our case, which may actually also just be a problem of the electrodes that we attached, we saw some spikings in our recordings, which I don't know yet where they're coming from. And I would also like to echo that I also see or would have concerns regarding the changing of the montages, and I would already express my interest in the switching box. I see myself being the first creating human errors with disconnecting or falsely connecting these electrodes. And the other thing I would like to quickly talk about is the staircase procedure that's implemented on the device. Because so I was the one sending the example code to Nir, and I think they only made little changes with respect to the code. And so due to the way it's created, it was created before the device actually existed and before the GUI existed. So there are some things that came from that. The staircase currently runs directly on the Arduino, and that limits the range of applications because you cannot do fancy analysis, curve fitting, or these kinds of things. So it's currently an X up, Y down staircase, so you can decide how many correct or false responses someone has to make until the staircase adapts, which then would give you a dedicated target performance. And we should also decide on what actual target performance we want to have, because with a one up, two down, no, two up, one down staircase, you would end up with 70% performance, and with a one up, one down, you would end at 50%. You can select a number of trials. You have to set stimulus duration and interstimulus intervals, base brightness and target brightness. And what I would also like to notice that there is an adaptive step size. So you start off with an initial step size. You can actually see that in this figure. You start up with an initial step size, which you can set actually to be quite large. And once people start having reversals, the step size gets smaller, so we get closer to the actual value. So if we want to avoid needing a lot of trials to get to the actual perceptual threshold, we can actually increase the initial step size to get closer, just as a note. And the target stimulus brightness that is then used for the actual experiment is computed as the average over the last 10 trials. That's this horizontal line that you see in the plot. What's very nice is the results are stored then into variables, so we can actually directly reuse them in the main experiment without needing user input in principle. Yeah, here are more details on this reduction in step size. So it's decreased by 50% after each reversal. What's currently not implemented is that it increases again if people end up creating a lot of false responses. And you've also seen that in multiple plots that the step size gets very small towards the end, which I could imagine might cause problems if someone does not immediately understand the task. You may have created or is inattentive or whatever and misses targets. You may create some reversals at high intensities, which then decrease the step size, and then it's getting very difficult to get down to the actual threshold levels. And so I just wanted to share these basic concepts on how it's currently working, because it might be worth discussing if we want to adapt or change certain aspects of this staircase, or implement it differently, or change some of the parameters. And that's basically what I wanted to share. And I summarized some discussion points here for you, which we could address. Thank you.
Thanks, Florian. Excellent.
All right. Oh, sorry.
No, that's good. So then should we just add the Birmingham, Glasgow experience before we, and maybe some insights from...
Well, actually, there's not
Rovereto?
much to add,
Yeah.
so I think we can just skip that in the interest of time, since we're already quite over time, right?
Yeah,
I mean,
yeah.
I can summarize it very quickly by saying that we tried to we just tried the device, whether it works or not, and we only managed to do it on my personal computer until now, because we do not have access to the labs. So and therefore we also didn't do too much testing, because it wouldn't be representational of what the actual experiment would be like. However, we will, when we finally get to the lab, we will install it on a Linux system, so we'll have that covered, since Florian mentioned that. And yeah, I mean, other than that, we mainly just implemented the things that were wrong for other people. Actually, I got a lot of help from Umair to set it all up and make sure that the labels are correct and all the titration and stuff works. But I don't really have anything to add to the update other than that.
Okay.
Okay, great.
Yeah, I can say that's pretty much the same for Trento. We did some technical testing and we encountered the problem that Florian reported and on the programming. And then later on, we will try to focus on the staircase. And as Florian reported, we encountered several problems trying to get the right measure. That's pretty much all. And also, sorry, one thing is you were locating the response box laterally. I would suggest to use it in the midline possibly, and with the subject resting arms, because otherwise it's going to be quite difficult.
Good point. Yeah, I mean, these are really the practical issues. We need to continue piloting in all the piloting labs. Also, whether we should have like an armrest so that they won't get tired over an hour, right? And then how to direct the cables. And I think that eventually, when we have decided on all the parameters, have solved all the open issues, that we should really create a kind of video tutorial that every participating lab is going to watch, and where we show exactly how the electrodes are prepared, where stuff is placed, so to get the setups as similar as possible in all the labs.
Yeah.
Okay.
Yeah. Sorry, just one thing. What we are doing here, Elena Tonoli is writing a report of what we are doing with pictures, and then we will post that report when we are ready.
Great.
All right.
Great. I have a slide to guide our discussion. I mean, we have like officially 15 minutes left if we take the break, 10 more. But so I would, that's okay, share my screen again and just show this screen. Can you already see it? I'm not going to go full screen to be able to add comments and just make notes. That's okay.
Yeah. So yeah, we can see the slide. It's great. Just to point out, there have been questions posted in the chat window.
Right.
So we should probably, we try to answer. So probably till you just go over your slide in order to structure the discussion, then we probably should address the questions in the chat room.
Yeah.
Make sense?
Yeah, that's good. So I'm not going to read out every point here. I mean, you can do it yourselves, but the big chunks are the behavioral task and setup, right? That needs to be tested, which includes lighting conditions. Carlo just brought up also dark adaptation time, the staircasing, all these kind of things. Then we have the tACS application, the montages, which might need to be adjusted, or the montage switching procedures, impedance, all these kind of things. Then the tACS signal recordings, the questionnaires, general procedure and timeline of the experiment, and maybe if you other things that I've just now put under miscellaneous, but which relates to also maybe some logistic things. How many of these Arduino boxes are we going to build? How many participating labs are actually going to purchase them to make sure that the costs are met? I mean, no one is making profit here, but it's also an investment. And how we may be able to ship them around so that not every lab needs to buy them. And then the analysis. So I think where we should end up after having all the practical issues solved and it is running smoothly in all the labs is to create, also in all the piloting labs, is to create at least one full data set per lab and send it to the central analysis, which is hopefully going to happen with Benedict. And then we can see whether the analysis is possible given the data. So whether everything is stored as we think it should be, and so whether we are missing any details or whether data quality is too bad or whatever, so that the analysis pipeline can basically also be fixed before we submit, right? So I think these are in principle the open issues. If I have missed any kind of bigger topic that needs to be solved before moving on means finalizing the stage 1 registered report manuscript, basically. Let me know if you have any further ideas. I'm just going to add this to the bullet points, and then we have a documentation of what we need to discuss and keep solving over the next weeks and months.
Okay, so yeah, we don't have a lot of time left, so I think we should just start the discussion and use the remaining time for that. So I'm just going to read out the questions. Shuga Shibusawa, I hope I pronounced it right, asked, how do you put the electrodes on the face? Only use 1020 paste. I think Till, you probably best placed.
I think I already answered in the chat that so with the 20 paste, it's pretty easy. It's very sticky itself, so it just sticks to the skin. But to be sure, I guess we should just have a bit of tape, and then it's done. So we don't need any straps or so. And also this net bandage is just to keep everything nice and tidy and keep the pressure, but it's not necessary. So they will not fall off in my experience.
Right. Carlo, you asked about adaptation.
Yeah, I was wondering because, I mean, I guess in this case, roads are mainly involved. So it takes about half an hour for roads to get adapted. So I wonder, when did you start the task after subject being in the dark room or whatever? So, well, consider that the maximum adaptation happens in 30 minutes, but then probably by 5 minutes you reach a good level, 5-10 minutes.
But I think we're going to use a dimly lit room, not a completely dark room, right? That's
Yeah.
Oda said, otherwise the LEDs are too bright.
And actually, maybe even we don't need to dim it at all. Maybe we just need to make sure that there's no bright light in front of the subject in the field of view, not some kind of extra lighting in the room. But if it's just ambient light, it can be relatively bright because the electrodes, so the LEDs are so bright. And then we don't need to just go down to 10% of the luminance from the very beginning.
I mean, in how far is that really important, other than, of course, the subject being uncomfortable? But because the staircasing takes care of that, right? So if we naturally will have different lightnings in the different labs because of daytimes and whatnot. But other than the subject not being comfortable, I don't see a problem with that because we do adapt, right?
Yeah, but if you don't change room, yes, as long as the subject is adapted, that should be fine.
But the adaptation takes time, right? So the darker the room is, the more adaptation time we would need, the more uncomfortable it is, the lower the performance may be, the more difficulty that they may have actually focusing on the questions in between. They might need lighting, actually light to fill it out.
But if you have to do the whole setup of the electrodes and everything. So if you do that in the same room and have the same lighting, then that shouldn't be a problem. You just shouldn't have the bright lights on while you set the electrodes and then dim everything down right before the experiment, right?
Yeah.
Right. I think that's that's a very good point. So we should make a note in the protocol that the lighting should not be changed once the subject has entered the room. Yeah, we should absolutely note that. Till, are you noting that?
Yeah.
Fantastic. Benedict had a question. Benedict, maybe you just want to unmute yourself and ask the question. It's a long one.
Yes, it's a long one. So let me try to. Yes, it concerns the control conditions. I think we should be careful to not have stronger stimulation in those control conditions than in the occipital condition. Because what we want to do is to show if we have an effect in the occipital condition, we want to show that it's not due to retinal stimulation, right? So for that, we need a condition where we have the same amount of retinal stimulation, but no neural stimulation. We need the same amount of stimulation. If we have more, then we might see an effect in the retinal stimulation and also in the occipital stimulation, and then we don't know what we see in the occipital condition is that now also retinal stimulation, or is it a true effect? And from both the modeling results and from Till's results, it seemed like there's more retinal stimulation in the retinal control condition, right? You said yes, you didn't manage to produce phosphenes, right, in the A montage.
Yeah. Okay, I see the point. So I mean, in the retinal montage, we will have still, we can set it to 90% of that to make sure that there's no phosphenes. But if we cannot find the retinal threshold for the occipital montage, then we cannot set that to 90% as well, right?
Yes.
But
exactly.
the thing is, we cannot do that in any case, because unless we would do two main experimental conditions, right? Because we have to take care of two thresholds, the cutaneous and the phosphine threshold. So we're actually lucky that we might only need to take care of one of them, because it always happens earlier. But I wouldn't see a way around that.
Yeah, but that's exactly the problem, right? At the end, we will have like one value for each condition, which shows us how strongly is the detection modulated by tACS phase. And then if we have retinal stimulation only in one condition, then that value might be very high just because of that. And then what do we do? We might be lucky and that value is low, but we don't know.
So empirically, I don't see a way out, because we may not be able, because this occipital montage is so well designed that it doesn't produce strong retinal intensity, and it would become really unpleasant cutaneously before we start seeing anything in the retina.
Yeah.
We might, though, have help from Axel. I don't know, Axel, you want to comment? Is it possible to do this on the simulation side to try and match it more precisely?
Yeah, maybe we can model and have the same. In Modulate, have the same retinal stimulation in both conditions.
I would say it's a matter of interpretation. So how we interpreted the results. So if, let's say, and of course we document everything in the occipital montage, we do not have phosphene threshold. We don't perceive phosphenes, and then we operate the phosphene montage in a threshold level. So this is just above what was the experiment, but not too high. Then I think it's a nice control by itself. So we said even if it's higher, but it's higher just to the level of perception, but not more than that. That's that, and then we just deal with that in the interpretation level.
I guess it depends on whether you get positive or negative results, right? If you get nice effect for the occipital montage, but not for the others, you're home free. But if you actually have results, like if you see entrainment effects for the retinal stimulation, then it's really difficult, because then this potential alternative explanation comes into play that Bendik mentioned.
But how, as you said, how you can go around it, even with modeling. Modeling has its limitation. I mean, that's why we design it as experimental control condition, and deal with that in the interpretation. I mean, it could be the interpretation would be, hey, we in the experiment, subjects did not report phosphene threshold, and we have an effect, but the effect can be mediated, which is what if there is a phosphene effect, then you can mediate by that. That could be the maximum we can conclude out of that. And if there is a big difference between them, let's say if there is an effect, but the effect differs statistically between them, then it allows you to argue against that. I mean, we want to control.
So how would you interpret the results if we have the same amount of phase modulation in montage A and B?
So I would suggest that we look at the phase, right? So what you are suggesting, Benedict, and of course it makes sense, is that when we stimulate the retina, it will also influence visual perception. But that route is an indirect route, right? Whereas the occipital montage should target the cortex directly. Therefore, the phasic modulation should happen at different phases. So we can take that into account and actually pre-register the hypothesis that should we see a phasic modulation in the phosphene threshold condition, then we expect it to happen at a different phase than the actual occipital montage.
That would actually be a nice supplementary hypothesis, I'd say. We might also, I mean,
maybe I'd like to comment. I mean, I think the best thing we could then do is to, I mean, the problem is that the occipital montage, the Montage doesn't induce phosphines, right? So the best thing which we can do is basic, and then the interpretation would be, well, maybe it still has an indirect effect because we might have unconscious perception or unconscious modulation of the retina, which then still drives the effect. So the best thing which we then can do is have an additional control condition where we actually determine the phosphine threshold for the retinal montage and then go, for example, to 90% of that. That would then mimic that effect and then test whether we see anything.
Isn't that exactly what we do?
Yeah.
But how do you know that it mimics that? How do you know that we are at 90% in the occipital condition? Maybe we are 30%.
Well, but when we are at 30%, then it's even more unlikely that you get anything unless you believed in strong nonlinear effects of retinal currents through the retina.
So you control for the worst case scenario, essentially. Yeah. So if there's no perception, so as Axel said, you take, let's say, 90% of the threshold, which is close to the worst case scenario of no perception, and then it's a control condition, and then we can decide how to
exactly.
Yeah, but if we control for the worst scenario, we might produce false negatives.
So what I don't really see what speaks against acknowledging that there is or that there likely might be a phase modulation in the retinal control stimulation, but that phase modulation should happen at a different phase compared to the occipital montage. What is the problem with that?
No, that's good.
And maybe once we use the EMLA cream, which we didn't do here, we might be able to reach the phosphine threshold actually also for the occipital montage. Yeah. That's just a guess. I mean, we have to test empirically. If that's the case, then at least in those labs using EMLA cream and thereby reaching the phosphine threshold before they reach the cutaneous sensation threshold, maybe this will help to disentangle these effects.
Yeah. So I was a bit when you gave your presentation, Till, it's a bit related to that because it's also about the retinal control stimulation. So I think overall it looks very good. Like it looks like the whole thing is basically feasible. We just need to tweak around little parameters maybe, but in general there are no roadblocks we came across. So that's good. Just to say, you know, that this is going good so far. But what I thought is a matter of worry is if the noise in the tACS signal, right? And the whole analysis all hinges at so the whole analysis hinges at being able to relate the presentation of the stimulus to the phase of tACS. So the EEG electrodes that record the tACS artifact are very, very crucial indeed. So if we expect the strongest entrainment in that condition that also gives us the cleanest phase signal, that strikes me as a possible confound, right? Because in that's scenario someone could say, okay, you don't find the phase modulation in the retinal condition, for instance, simply because you have more noise in your measures.
So it's I think that's really not a problem at all, because what's different to like noisy EEG or so is that we know in the background is a perfect sine wave at a fixed frequency all the time, like for minutes and minutes and minutes. So no matter how noisy the signal is, it could be really, really noisy. We just need to fit a sine wave over like minutes, and we would have a perfect signal to extract phase from.
Sure, but
right?
Any fit is always as good as the data it's fitted to, right? Isn't it? So if you have a noisy data,
in that case,
then your fit can be slightly off, and hence your phase measure will be slightly off.
Even if it's slightly off.
Guys, I think there's really no need for us to operate in a low SNR. This is a huge signal. We should be able to capture that. So it seems like we are not in the optimal configuration for our measurements electrodes. And I think maybe Axel, that's something for you. You can basically advise us I mean, of course, we can do it experimentally and test it, but maybe Axel can do this exercise, just kind of explore where will be the best place to put the recording electrode, differential recording essentially, to capture it, to capture this waveform. Yeah, and I think, I mean, what we heard, there's kind of Florian, there's two extremes. One extreme that we're actually saturating essentially the recording, which will be bad as well because you won't see the waveform. And the other one, you have a small signal. So 5 microvolt, as you can, millivolt, as you can see here, is still small. We should be able to go above that. So I think by optimizing the electrode configuration, so where to position that, and as well, this is something we can potentially do, adding some kind of attenuator. So maybe some kind of a manual attenuator that if the signal is too high, people can just switch it on or connect to that, and that will kind of dump by a factor of 10, let's say, the voltage or something like that. Of course, we can do more than that. We can add more gain into the recording. It's a differential amplifier. We can do that. We didn't think it would be necessary given the magnitude of that. So maybe after optimizing the configuration, based maybe on Axel's suggestion, if the signal is still small, and we should define a range of good signal. As you can see here, 50 millivolt is a good one. We should see if it's realistic to get it. If not, we can adapt the hardware accordingly as well. Yeah.
I have a question there. Why do you put it on the skin at all? Do you think there might be phase shifts because of the gel or something like that?
That's a good question. I mean, that's as far as I suggested to sample it directly from the, put like a resistor in series and sample that. But as far as I understand, some labs will have issue with that in the context of the ethics. That was the problem.
That was the only issue.
But for me, it's the other way around. I would have issues to connect a self-built device to the human, and I have an output on my stimulator that I can feed into the Arduino without ethic problems. Yes, but would that be a problem? Is anybody objecting if some people record the pseudo EEG from the tACS and others record it from the scalp?
No, I think technically that's the preferred solution.
Yeah, just this remote, this output channel, I think it's another $5,000 if you buy it from the company or so. So it's therefore most labs won't have it, but yeah, that would be preferable.
Yes, because I mean, yeah, if we can do that, that's perfect, Christoph. So any lab that can do that, I think should do it that way. If you record the artifact with EEG electrodes, then I think the preferable solution is to find a montage. And that's probably something for us to pilot, but to find a montage where the signal to noise ratio is equal between the conditions, comparable.
We could also just wrap a little bit of coil around the cable and just measure the current via induction without interacting at all with the circuit.
We can do that. That's a good idea, Tim. Yeah, we can do that. We can have a current monitor.
Because it's not shielded, the cable, right? So
will not
well,
be
if
very
that's
large
something that works for people, we can look in making that. I think it's a good idea. Then you don't have all this kind of variability. You get the full signal. Of course, I'm
a little bit skeptical there. You can try, but the voltages with that which you induce by that low at this low frequencies might be very small.
Yeah, this was exactly what I think. It's actually 10 hertz or so. This is low frequency. I mean, we need to we can explore that. We're happy to do that.
So we will keep piloting it, and maybe even just twisting the cables will solve a bit of the issue, because we don't know where the noise comes from. It could be external noise, could be muzzle, could be from the simulator. But I think we just do a bit more practical piloting, see whether it's very easy to get good signal to noise ratio with this method. And in parallel, we can think about whether we want to explore separate technical solutions.
Yeah. I think we're 10 minutes over time already. So probably we should wrap up. Yeah, I would like to thank everyone for contributing. everyone for participating, in particular Till and Christoph for piloting this, Nia for building the box and shipping it out and making it work. So that's all great. So I guess, yeah, as I said, if you're interested, if you're watching this and you think, oh, this is something I really would like to be involved in, then please do email us. The email address is tacschallenge@gmail.com. Follow us on Twitter and watch this space. All right. Bye, everyone.
And we all keep in touch via Slack anyway.
Absolutely, we will. Yeah.
If you want to keep discussing this, there's a space dedicated for discussion in Gather Town, so you can just get there and discuss.
Right. I might grab dinner first.
By the way, Carlo, Gather Town is really cool.
Yes.
Bye.
All right.
Bye.
Thanks, everyone. Bye-bye.